Tonight, we're going to look at the most powerful invisible objects in the universe. A black hole does not shine from a surface, reflect the light that reaches it, or announce its boundary with a material wall. Its defining edge is an event horizon, a limit in space-time beyond which no path leads back to the outside universe. Matter can cross it, light can cross it, but once either has passed inward, nothing, not even light, can return. That sentence makes a black hole sound like an object defined entirely by absence. In practice, black holes are found through presence. A nearby star moves around an unseen mass. Gas circles faster, heats, and releases X-rays. Light from behind the object bends into arcs. Two compact bodies merge and leave a tremor in space-time that reaches Earth after traveling for more than 1 billion years. The black hole remains dark, while everything around it becomes evidence. Every one of those signals comes from outside the horizon. That geographic fact will keep the story honest. The X-ray photon left before the gas crossed. The orbiting star remains far beyond the boundary. The gravitational wave was generated by the evolving space-time around merging horizons and continued outward. Even the famous ring images show radiation navigating the exterior. The interior is not secretly photographed inside the data. It is constrained by a theory that succeeds around it, then hidden by the very causal boundary the theory predicts. But what gives this invisible object its horizon? What would happen to light and time near that boundary? And how can astronomers measure something that does not emit an image of itself? By the end of tonight, you're going to understand exactly how black holes form, what their visible surroundings reveal, and where the tested predictions of relativity give way to questions that physics has not yet answered. Before we get started, if you love exploring black holes as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Keep one distinction nearby for the entire journey. A black hole is not a hole cut through space. It is a region where mass and energy have curved space-time so deeply that the future points inward past a boundary. Its power is not a distant suction. It is geometry. The same gravity that keeps a planet in orbit becomes near enough to a sufficiently compact mass, a one-way arrangement of possible paths. From a distant orbit, you would feel only the mass, not a special pull on your path. The first problem is the name. The word hole suggests emptiness, an opening where matter has been removed. A black hole is nearly the opposite. It is an extreme concentration of mass. The darkness comes not from an empty center, but from the inability of light to escape once it crosses the event horizon. From far away, the object's gravity behaves like the gravity of any other object with the same mass. Distance softens the field. Orbits remain orbits. The unusual behavior begins when the mass is compressed inside a small enough region. This is why a black hole is not a cosmic vacuum cleaner. If the sun could be replaced by a black hole with exactly one solar mass, Earth would continue around that mass in essentially the same orbit. The planet would lose sunlight and solar heat, but it would not suddenly spiral inward merely because the central object had become dark. Gravity at Earth's distance would still be set by the same central mass. The difference would be concentrated close to the new horizon, only a few kilometers from the center. The orbit example also separates mass from size. The present sun distributes one solar mass through a sphere nearly 1.39 million kilometers across. A one solar mass black hole would place that mass behind a horizon only kilometers wide. At Earth's orbit, the two fields can look alike. Near the center, they cannot. One object has a hot plasma interior and a visible photosphere. The other has no material surface and permits stable exterior descriptions only down to specific relativistic limits. The event horizon is also not a shell. It has no steel-like thickness and no landscape resting on it. It is a boundary in cause and effect. Outside it, some path through space-time can still lead away. At the horizon, the outward route closes. Inside it, every future directed route remains deeper within the black hole. A falling object does not strike the horizon in the ordinary sense. It crosses a location where the structure of possible futures has changed. The material visible in familiar black hole illustrations lies mostly outside that boundary. A luminous accretion disk is orbiting matter. A bright corona is hot plasma above the disk. Jets begin in magnetic fields and moving plasma near the black hole, not from material climbing out after crossing the horizon. The dark center in an image is a shadow produced by captured and redirected light, not a photograph of an interior room. This separation protects the explanation from a common confusion. A black hole can be dark while its environment is among the brightest places in a galaxy. The darkness describes the horizon. The brightness describes matter that has not yet crossed it. Between those two facts sits nearly everything astronomers can measure. To follow the geometry, you can begin with one path that feels locally straight. The next step is to replace the idea of gravity as an invisible rope. In general relativity, mass and energy shape space-time, and space-time guides the motion of matter and light. A planet follows what is, locally, the straightest available route through curved geometry. Light does the same. Near Earth, the curvature is small enough that ordinary descriptions work well. Near a black hole, the curvature becomes central to every observation. This curvature does not need a downward direction outside the universe. The familiar rubber sheet picture is only an analogy, useful because it turns geometry into a visible slope. Real space-time has 3 dimensions of space joined with time. The black hole changes intervals, paths, clock rates, and the relationship between events. What looks like a falling trajectory from one observer's coordinates may still feel locally like free motion to the traveler following it. The equivalence principle gives the traveler a local foothold. Inside a small, freely falling laboratory, objects float together and ordinary non-gravitational experiments behave as though gravity has been removed. The laboratory is still moving through curved spacetime, so observations across a larger region reveal tides. This distinction between local freedom and global curvature explains how a traveler can feel weightless while following a path that, on a distant map, descends toward a horizon. Light reveals the geometry because its path bends around mass. A distant star seen near the black hole's position can appear shifted or multiplied. Light from the back of an accretion disk can curve around the hole and arrive from above or below the apparent shadow. Some rays make partial loops. A much narrower set can circle more than once before escaping. The image becomes a map of possible paths rather than a simple view through transparent space. Time is part of the same geometry. A clock held deep in a gravitational field runs more slowly relative to a clock far away. Light climbing outward loses energy and shifts toward longer wavelengths. These effects are not added after the spatial bending. They are different views of one space-time structure. Near an event horizon, their strength makes ordinary language feel unreliable because words such as now and distance depend on the observer and the coordinates being used. The event horizon is therefore not defined by a force meter reaching a particular number. It is defined globally by whether signals can reach the distant future. A traveler can pass a location without detecting a solid boundary, while the complete spacetime says that no later signal from that traveler will reach an outside observer. The black hole is an object whose most important surface is written into the geometry of communication. On a map, you could place the simplest solar mass horizon across part of your city. For a non-rotating black hole, one number provides a first scale. The Schwarzschild radius is about 3 kilometers for each solar mass. Compress the mass of the Sun inside a sphere with a radius of roughly 3 kilometers, and the boundary of that sphere would become an event horizon. The present Sun has a radius near 696,000 kilometers. The comparison is not a proposal for squeezing our star. It is a measure of how extreme compactness must become. The scaling is linear. A black hole containing 10 solar masses has a Schwarzschild radius of roughly 30 kilometers. A million solar masses gives roughly 3 million kilometers. Increase the mass and the horizon grows in direct proportion. Density does not scale the same way. A larger black hole can enclose vastly more volume, so its average enclosed density can actually be lower than that of a small stellar black hole. The calculation comes from setting the classical escape speed expression equal to light speed, though the full interpretation belongs to relativity rather than a projectile fired from a surface. Written compactly, the radius is twice the gravitational constant times mass, divided by light speed squared. The equation contains no separate term for color, composition, or stellar history. Once the simple non-rotating exterior is specified, mass fixes the horizon scale. The biography matters for how the hole formed and spins, not for adding a conventional texture to its edge. This leads to a result that seems backward. The tidal difference across a human-sized object at the horizon can be severe for a small black hole and comparatively gentle for a supermassive one. The large horizon places the crossing farther from the central region in a geometric sense. A traveler near a stellar mass horizon may be pulled unevenly from head to foot with destructive strength. At the horizon of an enormous black hole, that local gradient can be much smaller, even though return remains equally impossible. Rotation changes the exact geometry. Real astrophysical black holes are expected to spin because their parent stars, accreting gas, and merger partners carry angular momentum. A rotating black hole is described by a different solution, commonly associated with the name Kerr. Its horizon size and surrounding regions depend on mass and spin. Yet the 3 kilometer per solar mass figure remains a useful quiet ruler for the simplest case. Return to that ruler whenever the later numbers become large. A 10 solar mass black hole is not a dark sphere the size of a star. Its horizon can fit across a region comparable to a city. A black hole of billions of solar masses can place its horizon on the scale of a planetary system. The same underlying relationship connects both. Mass sets the scale. Compactness creates the boundary. Watching the star's final balance, you would see gravity outlast each temporary source of support. Stellar mass black holes begin with stars that were born heavy. During most of a star's life, energy released by fusion helps maintain pressure against gravity. The balance is not stillness. Gravity pulls inward at every moment, while the hot interior supplies an outward response. As the star changes its fuel and builds heavier nuclei, that response becomes harder to sustain. The final structure depends on the star's initial mass, composition, rotation, mass loss, and interactions with companions. When a sufficiently massive stellar core can no longer support itself, it collapses. Outer layers may be expelled in a supernova, or a star may undergo a quieter form of direct collapse with less visible display. The remaining core can become a neutron star if compact matter supplies enough support. If the remnant is too massive for known support mechanisms, collapse continues toward a black hole. NASA's broad description places the relevant crushed core above roughly 3 solar masses, though the exact pathways remain subjects of stellar modeling. The threshold is not identical to the original star's birth mass. Massive stars lose material through winds, eruptions, and transfer to companions. Metallicity affects those winds. Rotation alters mixing and the core. A star born with more than 20 solar masses may finish with a remnant far lighter than its initial body, while binary exchange can strip or enlarge the core. This is why astronomers model populations rather than assigning one birth mass to one inevitable final object. The new black hole inherits more than mass. It can inherit angular momentum, and it may receive a motion through the galaxy from asymmetries in the collapse. If a companion star survives, the pair can become an X-ray binary. If the original star was isolated, the black hole may travel through the Milky Way with little nearby material to make it visible. Darkness then becomes an observational problem rather than an absence of gravitational influence. The phrase stellar mass covers a population, not one standard size. Observed black holes range from a few to dozens of times the sun's mass, while gravitational wave detections have expanded the known distribution and revealed merger remnants in heavier ranges. The birth mass can be altered later by accretion and by mergers. A black hole is therefore both a remnant and a growing record of what it has encountered. Nothing about this formation requires the entire original star to fit inside the final horizon at once. The core collapses first. Outer matter may escape, remain in orbit, or fall inward later. The horizon belongs to the compact remnant. The visible explosion, when one occurs, belongs to material outside it. Once again, black hole astronomy begins by separating the invisible object from the luminous events nearby. Beside the visible companion, you would infer the dark object from motion before light. For decades, one of the clearest ways to find a stellar black hole was to watch a visible star behave as though it had an invisible companion. The star shifts toward and away from Earth in a repeating pattern. Its spectrum moves slightly blue, then red. From the period and speed of that motion, astronomers estimate the mass required to hold the orbit. If the unseen companion is too massive to be a neutron star and emits no ordinary starlight, a black hole becomes the strongest explanation. Some binaries provide a second signal. Gas from the visible star can cross the space between the objects and curve into orbit around the black hole. It does not fall straight down. It carries angular momentum, so it forms a disk. Collisions, turbulence, and magnetic stresses move angular momentum outward, while matter drifts inward. Gravitational potential energy becomes heat, and the inner disk can reach temperatures that produce intense X-rays. The visible star can supply matter in more than one way. A strong stellar wind may be partly captured. In a tighter system, the star can fill a gravitational region called its Roche lobe, allowing gas to stream through the balance point between the bodies. The pattern of transfer changes with the orbit and stellar evolution. A black hole that appears quiet today can brighten when the supply changes, while an active system can enter a faint state without its central mass disappearing. An X-ray telescope sees the changing brightness and spectrum of this flow. An optical telescope measures the companion star. Radio observations may reveal a jet. No single measurement needs to show the horizon directly. The mass, orbit, high energy emission, and compact scale reinforce one another. The black hole is reconstructed from a system whose visible parts respond to an unseen center. Cygnus X1 became an early and enduring example of this method. A massive visible star orbits a compact X-ray source. Decades of measurements refined the distance, orbital inclination, and component masses. The details changed as instruments improved, which is part of the lesson. Black hole claims are not labels applied once. They are models tested against motion, spectra, timing, and geometry, then revised when the measurements become more precise. The binary also corrects the image of a black hole, roaming constantly in search of material. Accretion requires a supply. In a close binary, the companion provides one. In isolation, the same black hole can become faint. The horizon has not weakened. The environment has simply stopped illuminating it. Following one parcel of gas, you would watch it circle many times before moving inward. An accretion disk is not part of the black hole. It is matter negotiating with gravity outside the horizon. Each parcel of gas has sideways motion, so it circles rather than falling radially. To move inward, it must transfer angular momentum elsewhere. Magnetic turbulence can link neighboring regions of the disk. The inner region loses angular momentum and descends. The outer region receives it and shifts outward. Through that exchange, the disk converts organized orbital motion into heat. The energy release can be highly efficient because the inner orbit lies deep in the gravitational field. Gas can radiate a significant fraction of its rest mass energy before crossing the horizon, depending on the black hole's spin and the disk's structure. The brightness belongs to the loss of orbital energy, not to combustion on a surface. There is no hard ground where the gas lands. Its luminous history ends as it passes beyond the region from which photons can escape. The innermost stable circular orbit supplies an important boundary outside the horizon. Beyond it, nearly circular paths can persist. Within it, idealized disk matter can no longer maintain the same stable orbit and begins a faster plunge. The location depends on spin and whether the orbit follows or opposes that rotation. Astronomers cannot place a ruler there, but the disk's thermal spectrum, reflected X-rays, and variability can constrain how close the luminous flow approaches the black hole. Temperature changes across the disk. Cooler outer material may glow in visible or ultraviolet wavelengths. Hotter inner regions can produce X-rays. The spectrum becomes a layered record of radius, temperature, composition, motion, and viewing angle. Short changes in brightness reveal compact scales because a region cannot coordinate a fluctuation faster than light can cross it. Timing becomes another ruler placed around an object that cannot be directly lit. The disk's apparent shape is altered by lensing. Light from its far side can arc over the black hole, making the disk appear to wrap around the shadow. A second image can appear below. If the disk is tilted, Doppler beaming brightens the side moving toward the observer and dims the side moving away. The familiar asymmetric ring is therefore not merely a painted circle. It is an encoded combination of motion and curved spacetime. Some black holes possess no steady disk. Some accrete in bursts. Some are fed by a companion. Some by gas near a galactic center. And some by the debris of a star torn apart on a close passage. The horizon can be similar, while the surrounding display changes enormously. The black hole remains the dark term in a luminous equation. If your eyes could register X-rays, you would still see only the exterior plasma. The disk is not the only source of light. Above its inner region, astronomers infer a hot, tenuous corona threaded by magnetic fields. NASA describes black hole coronae as turbulent clouds that can reach temperatures near 1 billion degrees. The density is low, but the particles carry high energies. Lower energy photons from the disk pass through this environment and can gain energy through repeated interactions, emerging as harder X-rays. The corona's exact shape remains uncertain. It may be compact near the black hole, extended over the disk, or connected to the base of a jet in ways that change with the accretion state. X-ray spectra carry clues. Some photons travel directly outward. Others strike the disk and produce a reflected spectrum containing broadened atomic features. The strong gravity and rapid orbital motion stretch those features into shapes that encode conditions close to the horizon. Iron supplies one widely studied feature. In relatively calm laboratory material, fluorescent iron emission occupies a narrow energy range. Near a black hole, orbital speeds produce Doppler broadening. Deep gravity shifts photons toward lower energy, and lensing changes which regions contribute to the observer. The line can acquire a wide asymmetric profile. Interpreting that shape requires assumptions about illumination and disk structure, but it offers a spectrum-based route to scales no direct image can resolve. Brightness can echo. A change in the corona reaches the observer directly, while the reflected response arrives after traveling down to the disk and back out. The delay can be measured. Because light speed sets the conversion from time to distance, these reverberation lags provide a scale for regions too small and distant to resolve as pictures. A fraction of a second in a stellar system can describe distances of thousands of kilometers or less. Black hole astronomy therefore operates across many kinds of light. Radio waves can trace jets. Infrared and visible observations can follow stars and cooler gas. Ultraviolet light can reveal hotter disk regions. X-rays probe the inner flow and corona. Gamma rays can appear in the most energetic environments. Each band isolates a different part of the system, and together they keep the unseen mass from becoming an unconstrained idea. This is the first major answer to the opening puzzle. Astronomers do not need the black hole to shine. They need clocks, spectra, orbits, and paths. Darkness removes one direct signal, but gravity writes itself into every surrounding measurement. No single wavelength supplies a complete diagram. Dust that blocks visible light can become transparent in infrared or radio. A bright disk component can hide a weaker corona until timing or spectral shape separates them. X-rays may vary quickly enough to trace the smallest emitting regions, while radio lobes preserve activity across much longer intervals. The measurements are complementary because they respond to different temperatures, particle energies, and spatial scales. When several bands change together, astronomers can test whether one physical event connects them. When they change separately, the difference reveals distinct regions. Multi-wavelength astronomy turns one unresolved point into a system with structure, even when the horizon remains smaller than the telescope's image. Falling feet first, you would measure a difference between gravity at your head and feet. Gravity near a compact object changes over distance. The side of an object closer to the black hole feels a stronger pull than the side farther away. That difference is the tidal force. Earth raises tides in the moon, and the moon raises tides in Earth's oceans. Near a black hole, the same principle can become strong enough to stretch matter along the direction of fall while compressing it across the other directions. The informal name is spaghettification, but the underlying effect is a gradient in gravity. The gradient depends on both mass and distance. A small stellar black hole has a small horizon. Reaching that horizon means entering a region where curvature changes rapidly across a short distance. The difference between the pull at one end of a body and the other can become destructive before or near crossing. A supermassive black hole has a much larger horizon. At its boundary, the local change in gravity across a few meters can be far gentler. This does not make a supermassive horizon safe in the larger sense. Crossing remains one way. It only separates two questions that are often combined. whether local tides are immediately destructive, and whether a future path can return to the outside universe. A traveler could, in theory, cross a sufficiently large horizon without encountering a sudden material surface or an instantly fatal gradient, while still losing every possible route back. Tidal disruption can also happen outside a horizon. A star passing too close to a supermassive black hole may be pulled apart. Part of the stellar debris can escape, while part returns and forms a hot, changing flow. Telescopes observe these tidal disruption events as bright transients. Their rise, spectrum, and fading offer another way to study the mass and surroundings of a dormant black hole that had previously lacked a bright disk. The black hole does not reach outward with a special appetite. The star follows an orbit that passes inside a tidal boundary, just as a comet can pass too close to a planet, or a moon can cross a planet's disruption limit. What makes the black hole case extreme is compactness. A great deal of curvature is concentrated into a region small enough that neighboring parts of one star can be placed in very different gravitational conditions. The same gradient explains why mass changes the experience at the horizon. Tidal strength depends not only on total mass, but on how rapidly the field changes across the object's length. A larger black hole places its horizon farther from the center, where that local change can be smaller. A stellar black hole brings the boundary into a much tighter region. The event horizon remains equally one way in both cases, but the surrounding curvature is distributed across a different physical scale. This is one of the recurring lessons of black hole physics. A single phrase can hide two measurements. Escape depends on causal geometry. Stretching depends on a local gradient. They become extreme near the same object without reaching their extremes at the same place. Carrying an ideal clock, you would find every local second ordinary on your own path. The next change concerns time. Place one ideal clock far from the black hole and another deep in its gravitational field. When their signals are compared, the lower clock accumulates less time. This gravitational time dilation is not an illusion caused by a slow mechanism. Any reliable clock follows the same relationship, whether it counts atomic transitions, light pulses, or mechanical cycles. The geometry sets the comparison. Light sent outward from the deeper clock also changes. Each wave crest arrives farther apart than it was emitted. The light is gravitationally redshifted, losing energy as measured by the distant observer. Near the horizon, repeated signals arrive increasingly delayed and shifted to longer wavelengths. The falling source appears to slow, fade, and redden. In the distant observer's chosen coordinates, the horizon crossing is never seen as a clean final frame. The falling observer describes something different. In a large enough black hole, the traveler's own clock continues normally through the horizon. No universal alarm announces the crossing. Locally, free fall removes the sensation of weight, although tidal forces can remain. The traveler reaches the horizon in finite proper time. The apparent disagreement is not a contradiction. The observers divide spacetime into time and distance differently and do not reunite to compare notes after the crossing. Language becomes delicate here. Saying that time stops at the horizon can be useful only if the observer and coordinates are specified. The falling clock does not stop for its owner. Saying that an outside observer watches an object freeze forever also hides the practical fading. The signals become redder, weaker, and more widely separated until they are no longer detectable. What remains is a mathematical limit, not an indefinitely visible photograph. This observer dependence is one reason black holes teach more than strong gravity. They expose the fact that time is not a single river flowing identically everywhere. Clocks record paths through space-time. Near a horizon, two reasonable paths can produce profoundly different comparisons without either clock malfunctioning. The comparison always requires signals or a later meeting. Two nearby clocks can be synchronized before one descends, but the distant observer learns about the lower clock only from light that has climbed outward. Each received pulse carries both the clock reading and the redshift imposed by the path. This separates a local measurement from a remote inference. The traveler does not feel a personal second stretching into a longer interval. The remote station receives a sequence whose spacing has changed. General relativity connects the two accounts without declaring one universal clock to be correct. The same principle already appears in weaker form around Earth, where clocks at different altitudes accumulate slightly different amounts of time. A black hole horizon takes that measured relationship into a regime where the signal delay grows without a final outward message from the crossing. At the boundary, you would not collide with a wall or reflective shell. Return now to the event horizon itself. For a stationary black hole, the horizon surrounds a region whose future cannot communicate with distant space. It is one way because outward directed light at the boundary does not gain distance from it, and inside the boundary, every future directed light path goes deeper. An engine cannot solve this by pushing harder. The limit is not a shortage of thrust. It is the absence of an outward future route. From far away, this boundary can be described using the Schwarzschild radius for a non-rotating hole or a related horizon in rotating geometry. Close to the traveler, however, the horizon is not a painted sphere. It can be crossed without collision. Its significance depends on the complete future of signals, which makes it a global feature of space-time rather than a locally manufactured wall. Once matter crosses, the external black hole can still be described by a small set of measurable properties, especially mass, angular momentum, and electric charge. Astrophysical holes are expected to carry little sustained net charge because surrounding plasma supplies opposite charges. Mass and spin dominate the description. The detailed shape of the fallen object does not remain as visible structure on the horizon for a distant astronomer to inspect. The horizon can grow when energy enters. Add matter, radiation, or another black hole, and the total mass changes. In a merger, two horizons evolve into one. The newly formed remnant rings through distortions in spacetime and settles toward a stable rotating form. Gravitational waves carry away part of the system's energy and angular momentum. The darkness is dynamic, even though it provides no ordinary surface features. The central anchor remains simple. Nothing, not even light, returns after crossing. That claim belongs to classical general relativity and defines the horizon. Later, when Hawking radiation enters the story, the quantum prediction will require more careful language. It does not describe a conventional particle flying outward from inside the horizon. This is also why the horizon cannot be located by placing a single instrument at one point and asking it to detect a special substance. The instrument can measure curvature, acceleration, radiation, and tides. Determining whether it lies inside the event horizon requires knowing which future light paths reach distant space. In a stable idealized spacetime, equations identify that boundary cleanly. During collapse or merger, the geometry changes, and the complete causal map becomes more complicated. The definition remains precise even when the boundary is not a permanent sphere. It is the edge of possible communication. Matter can add mass and enlarge it. Two evolving horizons can become one. At every stage, the important distinction is not darkness as a color, but the set of futures that the spacetime permits. Looking toward the darkness, you would see a shadow larger than the horizon, hidden within your view. If the horizon emits no light, the dark region in a black hole image might seem equal to the horizon itself. It is not. The observed shadow is shaped by light rays that are captured or redirected in the curved spacetime around the hole. NASA's Anatomy Guide describes the shadow as roughly twice the size of the black hole's actual surface in the relevant image geometry. The exact appearance depends on spin, viewing angle, and the emitting material. Outside the horizon lies a region where light can follow unstable circular paths in the simplest non-rotating model. A tiny change determines whether a photon escapes, circles again, or falls inward. Rays from the surrounding plasma can loop around the black hole before reaching the observer. Each extra loop produces another highly compressed image. These nested images form increasingly thin, faint photon rings near the shadow's edge. The bright ring seen by a telescope is not necessarily one perfect mathematical photon ring. It includes emission from the surrounding plasma, blurred by instrument resolution and shaped by the flow. Theory and simulation connect that measured structure to the underlying spacetime. The central dark depression and the diameter of the ring provide tests of whether the compact object behaves like the black hole, predicted by general relativity. Because light can approach from the far side, the image contains directions that ordinary perspective would hide. The top of the disk can appear above the shadow. The underside can appear below. More strongly lensed copies collect close to the ring. Looking at a black hole, therefore, means seeing several paths from the same emitting matter, folded into one frame by gravity. This is why the first black hole images required more than a camera with a powerful lens. The angular scale was minute, the source changed over time, and radio signals from many observatories had to be combined. The image is a reconstruction from synchronized measurements, guided by careful calibration and tested across multiple imaging methods. It is evidence produced by an Earth-sized instrument. The word shadow can therefore mislead if it suggests an opaque ball blocking a lamp. Some rays disappear because the horizon captures them. Others are redirected away from the observer. Still others wrap around the black hole and add light near the edge. The darkness is a deficit created by this entire family of paths. Its diameter depends on the surrounding geometry and is larger than the horizon that caused it. Astronomers compare the measured ring and central depression with simulations that vary mass, spin, plasma structure, and viewing angle. Agreement across that range does not convert the orange emission into a photograph of the boundary. It establishes that the light behaves as expected around a compact object with a horizon-scale gravitational field. Tracing one arriving photon backward, you might find its source on the far side. Gravitational lensing begins well beyond black holes. Galaxies and clusters bend the light of more distant objects into arcs and multiple images. Near a black hole, the curvature is concentrated enough to create a more intricate map. A ray that began behind the horizon's apparent position can arrive from a direction above it. Another can pass below. The observer receives directions transformed by geometry. Consider a thin disk viewed at an angle. In ordinary space, its back edge would be partly hidden behind the central object. Around a black hole, light from that back edge bends upward and downward. The observer may see the far side as a narrow cap over the shadow and another image beneath it. The disk seems to stand vertically around the hole, even though the physical matter remains near one orbital plane. Motion adds another transformation. Gas on one side approaches the observer at a substantial fraction of light speed. Its emission is boosted and shifted toward higher frequency. Gas on the opposite side recedes, becoming dimmer and redder. The resulting ring can be brighter on one side without the disk containing more matter there. Brightness becomes a velocity measurement. Time also enters the image. Rays taking different paths have different travel times. A variable source can appear in delayed copies. Near a rapidly changing accretion flow, the reconstruction combines light emitted at slightly different moments. For Sagittarius A, whose mass is millions rather than billions of suns, the gas changes on timescales of minutes. That variability made imaging the Milky Way's central black hole a distinct challenge. Lensing is not a decorative distortion laid over a true picture. It is the picture. Telescopes record photons where they arrive and with the energy they carry. General relativity provides the paths connecting those arrivals to the emitting plasma. The dark shadow, bright ring, and repeated disk images are therefore a joint statement for matter and geometry. Different measurements help separate those ingredients. Total brightness tracks how much emitting plasma is present and how efficiently it radiates. Spectra divide that light by frequency. Polarization records the orientation imposed by magnetic fields and scattering. Changes over time reveal how quickly structures orbit, brighten, and fade. A geometric feature should persist in a different way from a temporary bright knot in the disk. The task is not to trust one attractive frame. It is to find the space-time scale that remains consistent while the plasma changes. This is particularly important for Sagittarius A, where the source can evolve during a single observing session. A reconstruction is strongest when motion, wavelength, and independent mass estimates all point toward the same compact geometry. Near a rotating hole, you would map paths that twist with the surrounding space-time. Astrophysical black holes are expected to rotate. Their parent stars rotate. Orbiting gas carries angular momentum, and merger partners circle before joining. In general relativity, a rotating black hole is described by Kerr geometry. Mass and spin determine the idealized spacetime when electric charge can be neglected. Rotation changes the horizon, the innermost stable orbits, and the way nearby paths twist. The rotating spacetime drags nearby directions around with it, an effect called frame dragging. Outside the horizon lies an ergosphere, where remaining stationary relative to distant space is impossible. Objects can still escape from this region, unlike from inside the horizon, but they must share some of the rotational motion. The boundary of the ergosphere is not the event horizon and should not be drawn as though the two were interchangeable. Spin changes how close stable disk material can orbit. For matter moving in the same direction as the black hole's rotation, the innermost stable orbit can lie closer than it does around a non-rotating hole. This allows more orbital energy to be released before the gas crosses the horizon. Spectra and timing near the inner disk can therefore carry information about spin, though the inference depends on models of the disk and emission. Theoretical processes can extract rotational energy from the region outside the horizon. Magnetic fields threading the nearby plasma may connect black hole spin to the power of relativistic jets. The details are studied through simulations and observation. It is safer to say that jets draw energy from the rotating system of black hole, disk, and magnetic field than to picture material being fired from inside the horizon. Spin also changes the appearance of the shadow subtly. The strongest distortion is moderated by the way light paths wrap around the hole, so even a rapidly rotating black hole can retain a nearly circular shadow from many viewing angles. Precise measurements are required. The large visual drama belongs mainly to the surrounding plasma. The test of geometry lives in small differences. There is no rigid crust carrying that rotation. Spin is a property of the spacetime and of the conserved angular momentum measured from outside. It is acquired through the history of collapse, feeding, and merger. Gas arriving in the same direction over long periods can increase it. Material arriving with changing orientations can produce a more complicated result. A merger combines the orbital angular momentum of the pair with the spins of the partners, while gravitational waves carry some angular momentum away. This gives spin the character of a fossil measurement. It does not preserve a visible memory of every event, but it summarizes part of the black hole's past. Disk spectra, timing, gravitational waves, and horizon-scale images approach that summary through different assumptions and different regions of the system. Following a jet outward, you would leave the horizon scale and eventually cross a galaxy. Some accreting black holes launch narrow jets in opposite directions. The jets contain plasma, magnetic fields, and particles moving at speeds close to light. They can remain collimated far beyond the scale of the accretion disk. In supermassive systems, radio-emitting structures can extend hundreds of thousands of light years, connecting a region near the horizon to lobes larger than the host galaxy's bright center. The black hole is not a nozzle with a hole through its pole. Matter that crossed the horizon does not reappear. The launch occurs outside, where rotating plasma and strong magnetic fields reorganize part of the inflowing energy. Some material continues inward. A smaller fraction is redirected outward. The system can therefore feed and eject at the same time without violating the one-way boundary. Relativistic motion changes what the observer sees. If one jet points partly toward Earth, Doppler beaming can make it much brighter than the opposing jet. The far jet has not necessarily vanished. Its radiation is de-boosted. In the most aligned cases, the source can appear as a blazar, whose brightness changes rapidly across the electromagnetic spectrum. Orientation turns one physical structure into several observational categories. Jets affect their surroundings. They inflate cavities in hot gas, drive shocks, and deposit energy far from the horizon. In galaxy clusters, X-ray observations reveal bubbles where radio jets have displaced the intracluster medium. This feedback can slow some cooling flows and influence where gas becomes available for future star formation. A compact dark object can regulate a volume many orders of magnitude larger than itself. That influence supports the roadmap title without turning the black hole into a supernatural force. Its power appears through conversion and leverage. Orbital energy becomes radiation. Spin and magnetic fields help drive jets. The jets reshape surrounding gas. The horizon remains invisible while the environment carries the consequence outward. The distance traveled by a jet does not mean the black hole exerts an undiminished pull across that entire length. The jet carries energy and momentum through plasma. It interacts with gas, expands, forms shocks, and can terminate in broad radio lobes. Each stage is local. The near-horizon system launches or organizes the flow. The moving particles and fields deliver the consequence outward. This chain explains how an object small beside its galaxy can influence gas far beyond its immediate orbit. It also explains why the effect is intermittent. Without a supply of accreting matter, the luminous disk can fade and the jet can weaken. Old lobes may remain visible after the central engine has changed state, preserving evidence of an earlier period of activity. Moving up the mass ladder, you would watch a city-scale horizon grow toward planetary dimensions. At the centers of most large galaxies, astronomers find evidence for supermassive black holes. Their masses range from hundreds of thousands or millions of suns to billions. The origin of the earliest and largest examples remains an active problem. Stellar remnants can grow through accretion and mergers, but observations of massive black holes in the young universe require efficient seeds and rapid growth. Several formation pathways remain under study. The horizon scales with mass. A black hole containing 1 billion solar masses has a simple Schwarzschild radius estimate of about 3 billion kilometers. That is a scale comparable to the outer planetary region of a solar system. Yet the host galaxy spans tens or hundreds of thousands of light years. The horizon remains tiny compared with the stellar system whose center it occupies. Supermassive black holes are measured through several methods. Astronomers track stars and gas orbiting a compact central mass. They model the speeds visible in spectra. They observe masers, X-ray emission, and reverberation in active nuclei. In 2 landmark cases, the Event Horizon Telescope resolved ring-like emission on horizon scales. The methods differ, but all ask whether a great mass is confined inside a remarkably small region. An active galactic nucleus is a feeding state, not a separate species of object. When gas reaches the central region, the accretion flow can outshine the surrounding galaxy. When the supply diminishes, the same black hole can become comparatively quiet. Our own galaxy's central black hole is currently faint compared with a quasar, though its neighboring stars still reveal its mass. Activity describes the environment and feeding rate. The black hole and galaxy develop together without a simple one-way script. Mergers bring gas, stars, and central black holes into new configurations. Accretion grows the hole. Outflows alter the gas available to form stars. Observed correlations between black hole mass and galactic structure suggest a shared history, while the exact causal pathways remain a field of research. The same mass can therefore appear under very different names in an observing catalog. A quiet galactic center may be measured from stellar or gas orbits. Supply it with a dense inflow, and it may become an active nucleus. Aim a relativistic jet near our line of sight, and Doppler beaming can make the system appear as a blazar. Place thick dust around the nucleus, and some wavelengths are hidden while infrared or X-rays reveal the buried source. These categories describe orientation, fuel, and environment more than separate kinds of horizon. The underlying supermassive black hole can remain while the visible identity changes over thousands or millions of years. Blackness is the stable center. Activity is the temporary weather around it. From Earth, you would locate the center by tracking stars through dust in your own galaxy. The Milky Way contains its own supermassive black hole. The compact radio source is called Sagittarius A, pronounced Sagittarius A star. Dust blocks an ordinary visible light view toward the crowded galactic center, so astronomers use infrared and radio observations to look through the obscuring material. What they found was not initially a ring. It was motion. Stars following tight, rapid orbits around a position that emitted no corresponding starlight. One star, commonly called S2, completes an orbit in roughly 16 years and passes close enough to the central mass for relativistic effects to be measured. Its path is not a perfect repeating ellipse in fixed space. The closest point shifts. Its spectrum changes with speed and gravitational depth. By following S2 and other stars over decades, teams reconstructed a mass of about 4 million suns confined within a remarkably small volume. The proof does not depend on seeing an event horizon. Keplerian motion supplies the first scale. Faster and tighter orbits require more central mass. The absence of visible matter capable of holding that mass in the observed volume rules out ordinary clusters as a stable explanation. Relativistic corrections strengthen the case. The result is a black hole measured through the geometry of nearby stellar years. Sagittarius A is quiet by quasar standards. It accretes only a small supply compared with the bright nuclei of distant galaxies. Yet hot gas near the horizon changes on timescales of minutes and produces flares. That rapid variability fits the compact size expected for a 4 million solar mass black hole. The environment is faint enough to be challenging and active enough to reveal structure. The Milky Way's center places the subject inside our own galaxy rather than in a distant category. About 26,000 light years separate Earth from Sagittarius A. The signals recorded tonight began crossing the galaxy when human civilization had not yet developed agriculture. The horizon itself remains dark, while the paths of stars and radio waves carry its scale across the intervening dust. S2 gives that scale an especially clear rhythm. Its orbit takes about 16 years, short enough that astronomers have followed complete revolutions rather than a small arc extrapolated across centuries. Near closest approach, its path departs from a fixed Newtonian ellipse and advances in the direction predicted by general relativity, producing a rosette-like precession. The measurement strengthens two conclusions at once. A mass near 4 million suns is concentrated at the common focus, and the surrounding spacetime alters the orbit in the expected relativistic way. No single star provides the whole case. Several stellar paths, spectra, and decades of observations converge on the same dark position. The black hole is mapped not by one photograph, but by a clockwork of moving points. Standing at one station, you would hold only a fragment of the planet-wide measurement. Resolving a horizon-scale structure from Earth requires extraordinary angular resolution. Building one physical dish the size of our planet is not possible, but radio astronomy provides another route. Very long baseline interferometry combines signals recorded at observatories separated by continents and oceans. With precise timing, the array behaves in key respects like a virtual telescope whose effective baseline approaches Earth's diameter. The Event Horizon Telescope observes at millimeter wavelengths. These short radio waves can probe compact structures near supermassive black holes while passing through some of the intervening material. Each station records enormous volumes of data alongside timing from atomic clocks. The recordings are physically transported to correlation centers, where computers align the signals and recover information about spatial structure. The array does not collect a conventional photograph pixel by pixel. It samples components of the source's spatial pattern at baselines determined by the positions of telescope pairs and Earth's rotation. The coverage contains gaps. Imaging teams use several independent reconstruction methods and test them on synthetic data. Features that persist across methods carry greater confidence than features produced by one set of assumptions. Atmosphere, instrument calibration, station weather, and the changing source all matter. For M87, the enormous black hole evolves slowly enough that a night's observations can be combined more readily. Sagittarius A changes within minutes, so the target can shift while the Earth-sized telescope is still gathering its view. Imaging it is closer to reconstructing a moving subject through a sparse global instrument. This method extends the theme of indirect visibility. The telescope measures radio correlations, not darkness itself. Algorithms reconstruct emission around a predicted shadow. Simulations connect plasma and spacetime to the image. The result is powerful because every layer of inference can be tested, compared, and constrained by data from a planet-wide network. Earth's rotation adds useful baselines as each pair of stations changes orientation relative to the source. Over an observing night, the array samples more of the spatial pattern than one frozen arrangement could provide. The gaps never vanish completely, which is why calibration and independent reconstruction are central rather than cosmetic. Timing must preserve the phase relationship between signals recorded oceans apart. Atmospheric water vapor can alter a millimeter wave path. A station failure removes particular baselines from the network. The final ring rests on controlling these ordinary complications with unusual precision. Calling the EHT an Earth-sized telescope is accurate as a description of its resolving baseline, but the phrase should not hide the distributed clocks, weather logs, data transport, correlation, and validation that make the virtual aperture work. Across 55 million light-years, you would receive radio waves shaped near a horizon far beyond your galaxy. On April 10, 2019, the Event Horizon Telescope collaboration announced the first image of a black hole's shadow. The target sits at the center of Messier 87, a giant elliptical galaxy about 55 million light-years from Earth. Its black hole has a mass near 6.5 billion suns. That mass gives the horizon an enormous physical scale and a large enough angular appearance to become one of the best targets in the sky. The published image shows a dark central depression surrounded by asymmetric ring-like emission. The ring is not the event horizon drawn in orange. It is radio light from hot plasma whose paths and brightness have been shaped by gravity and motion. The darker center is associated with the shadow. The brighter lower region reflects the structure and relativistic movement of the emitting flow. 6.5 billion solar masses can be replanted with the earlier ruler. At roughly 3 kilometers of Schwarzschild radius per solar mass, the simplest scale reaches nearly 20 billion kilometers in radius. Rotation changes details, and the image measures a shadow rather than the horizon itself. But the estimate explains why M87's central object can place horizon-scale structure across a region larger than our planetary neighborhood. The image tested the size and circularity expected from general relativity under the observational conditions. It did not reveal the singularity. It did not look through the horizon. It measured radiation from outside and found a central shadow compatible with a black hole of independently estimated mass. The achievement was a convergence of prediction, galaxy-scale measurements, radio engineering, and horizon-scale imaging. M87 also produces a prominent relativistic jet. On larger scales, radio and optical images trace the jet far beyond the tiny EHT field. The black hole's immediate environment and the galaxy-scale outflow belong to one connected system across an immense range of size. A ring measured in microarcseconds sits at the base of a structure visible across thousands of light-years. The first image was announced on April 10, 2019. But it represented years of preparation and analysis rather than one exposure taken that morning. The collaboration observed the source with separated radio facilities, compared reconstruction pipelines, and tested whether ring-like features could be artifacts of sparse coverage. The independently known mass near 6.5 billion suns supplied an external scale. The measured shadow supplied another. Their agreement is the important result. A beautiful ring alone would be suggestive. A ring with the expected angular diameter around a mass measured through other methods becomes a test. 55 million light-years of distance did not prevent the comparison because interferometry converted Earth's diameter into resolving power. Pulling back from the nucleus, you would see the outflow meet gas that never approached the horizon. The most powerful invisible objects in the universe are powerful partly because their surroundings amplify them. A supermassive black hole occupies a tiny fraction of its galaxy's diameter. Gas falling toward it releases energy. Magnetic fields organize some of that energy into winds and jets. those outflows reach clouds that would never approach the horizon and change whether the gas cools, escapes, or forms stars. In some galaxies, the nucleus shines as a quasar. The central light source can compete with or exceed the combined starlight of the host, even though the luminous region is far smaller. The energy comes from accretion. Matter descending through the gravitational field radiates before crossing the horizon. The black hole remains dark at the center of a source visible across billions of light years. Feedback can work in more than one direction. A jet can heat gas and prevent some of it from cooling into stars. A wind can clear material from the nucleus. Compression can also help trigger localized star formation under some conditions. The outcome depends on the gas, geometry, duty cycle, and energy. It is more accurate to describe regulation than to say every active black hole simply shuts a galaxy down. Black holes also merge when their host galaxies combine. Dynamical friction can bring the central masses inward through interactions with stars and gas. A pair may form, harden, and eventually enter the regime where gravitational radiation dominates the final inspiral. The full path from kiloparsec separation to coalescence contains open questions, especially for systems with little gas. The scale contrast remains the useful picture. A horizon might span a planetary system. A jet can cross a galaxy. Radiolobes can extend beyond it. The influence is not the horizon reaching outward. It is energy transferred through matter, radiation, magnetic fields, and waves in spacetime. Feedback often behaves like a slow control loop rather than a single explosion. Gas in a galaxy or cluster cools and begins to move inward. Some reaches the central accretion flow. The resulting radiation, winds, or jets return energy to the surrounding gas and reduce the supply that can cool. With less fuel, the active phase weakens, allowing cooling to resume later. NASA observations of massive elliptical systems describe this kind of heating and cooling regulation. The outcome differs among galaxies, and localized compression can accompany broader heating. The useful point is causal modesty. The black hole does not issue commands to the galaxy. Matter falls, energy is released, outflows interact with nearby gas, and repeated cycles accumulate into an influence visible on galactic scales. Between stellar and galactic scales, you would find a mass range only recently filling with evidence. For many years, observations clustered around two broad mass ranges. Stellar black holes contained a few to dozens of solar masses. Supermassive black holes contained millions to billions. The interval between them seemed sparsely populated. Astronomers proposed intermediate mass black holes from roughly hundreds to tens of thousands of solar masses, but compact clusters and uncertain mass estimates made individual candidates difficult to confirm. Several routes could build this middle class. Repeated mergers in dense star clusters might combine smaller black holes. Very massive stars or stellar collisions might leave heavy remnants. Stripped galactic nuclei might preserve a once central black hole after the surrounding stars are removed. Each pathway predicts different environments and mass distributions, so finding the population matters for both stellar evolution and the growth of supermassive seeds. Gravitational waves opened a new window. In the event called GW 190,521, the merger produced a remnant of about 142 solar masses. NASA describes it as the most convincing example to date of an intermediate mass black hole. The signal did not need the remnant to accrete gas or shine in X-rays. The masses were encoded in the changing gravitational wave pattern. One detection does not complete the census. Astronomers continue searching through cluster dynamics, tidal disruption events, X-ray sources, and additional gravitational wave mergers. Selection effects matter. A quiet black hole can be missed, while an actively feeding source can appear more prominent than the underlying population. The apparent gap may contain objects that are simply harder to identify. The 142 solar mass anchor shows how categories can emerge from events. Before the merger, the two components belonged to a heavier stellar range. Afterward, the remnant entered the intermediate class. Black hole populations are connected by growth. The mass ladder is not a row of sealed boxes, but a history of collapse, feeding, and combination. For GW 190,521, the inferred component masses were near 85 and 66 suns, with substantial uncertainty, and the remnant was near 142. The numbers do not add exactly because gravitational waves carried energy away, and because every estimate is a probability range rather than a perfectly weighed object. The heavier component is especially interesting because ordinary stellar models have difficulty producing black holes in part of that mass range through a single collapse. A previous merger inside a dense cluster is one proposed route, but the event does not preserve a visible label describing its ancestry. It supplies a measured waveform, a set of inferred parameters, and a formation question. Intermediate mass black holes have moved from a nearly empty category toward an observed population, but one prominent event is a beginning rather than a completed census. Listening to the translated signal, you would hear the final orbit accelerate into one rising sweep. Two black holes can form a binary in several ways. They may descend from two massive stars that evolved together. They may meet through interactions in a dense stellar cluster. Central black holes can pair after galaxies merge. However the pair forms, each body moves through the spacetime shaped by the combined system. Their orbital motion carries energy, and general relativity predicts that some of this energy leaves as gravitational waves. As energy and angular momentum radiate away, the orbit contracts. The black holes circle faster. The gravitational wave frequency rises, and the amplitude grows. This increasing signal is called a chirp because translated into sound, it sweeps upward. The name is an interpretation for human hearing. The detectors measure tiny changes in distance, not pressure waves traveling through air. Near the end, the horizons approach and merge. The process cannot be accurately described as two hard spheres touching. Space-time itself evolves nonlinearly. Numerical relativity solves Einstein's equations on computers to predict the waveform through inspiral, merger, and ringdown. After the common horizon forms, the remnant is distorted. It emits additional waves and settles toward a stable rotating black hole. The final mass is less than the simple sum of the two starting masses because energy has left in gravitational waves. The remnant spin reflects the original spins and orbital angular momentum. By matching observed signals to waveform models, scientists estimate component masses, spins, distance, and orientation, each with a range of uncertainty. The darkness becomes measurable through the precise rhythm of its changing geometry. Before direct detection, binary black holes were strong theoretical sources. After 2015, they became an observed population. Continued detections revealed systems heavier and more varied than the small sample known from X-ray binaries alone. A new instrument did not merely confirm an old object. It exposed a part of the population that light-based astronomy had difficulty seeing. The inspiral can last far longer than the portion heard by a ground-based detector. A widely separated pair loses energy slowly. As the distance shrinks, the loss grows, the orbit accelerates, and the remaining time collapses. Detectors are sensitive only when the signal enters their frequency band, so the recorded chirp is the final audible page of a much longer history. The waveform's rise is not an arbitrary sound effect added for drama. Its timing follows the changing orbital frequency, and its amplitude follows the moving masses and distance. Numerical models carry the calculation through the regime where two-body approximations fail. The final ring-down, then, asks whether the remnant behaves like one perturbed black hole. One signal joins three physical stages into a continuous test. Inside either control room, you would see your instrument register a change smaller than a proton. On September 14, 2015, the two advanced LIGO detectors recorded a short signal that passed first through Livingston, Louisiana, and then through Hanford, Washington. The waveform rose in frequency and amplitude before ending in a ring-down. Detailed analysis matched the merger of black holes of about 36 and 29 solar masses. The waves had traveled for about 1.3 billion years before changing the lengths of LIGO's arms by a minute fraction. Each LIGO observatory uses perpendicular arms several kilometers long. Laser light travels back and forth between suspended mirrors. A passing gravitational wave stretches one direction while compressing the other, then reverses the pattern. The change is smaller than a proton over the arm length. Isolation systems reduce ground motion, thermal effects, and other noise, while two separated detectors help distinguish a real traveling signal from a local disturbance. The signal was strong enough to be visible in filtered data without relying entirely on one detailed waveform template. Its frequency and rate of change constrained the system's masses. The final oscillation matched a black hole remnant settling after merger. LIGO's published physics analysis placed the holes only hundreds of kilometers apart near the end, circling in a regime where ordinary Newtonian descriptions were no longer sufficient. No telescope had to point toward a glowing disk. The black holes could have been electromagnetically dark. The detector responded to spacetime curvature arriving at Earth. This was the first direct detection of gravitational waves, and the first observation of a binary black-to-hole merger, joining two discoveries in one brief event. The date has become an anchor because it changed the available senses of astronomy. Before September 14, 2015, black holes were studied mainly through light and motion around unseen masses. After it, merging horizons could be heard through geometry itself. Each LIGO arm is 4 kilometers long, and mirrors make the laser light travel the effective path repeatedly before the beams recombine. The passing wave does not shove the entire observatory in one direction. It changes the relative lengths of perpendicular paths in an alternating pattern. LIGO describes the required displacement sensitivity as far smaller than a proton. That scale explains why one instrument is not enough. Environmental disturbances, instrumental artifacts, and calibration errors must be rejected. The matching pattern in two sites, separated in location and arrival time, supplied the essential cross-check. GW 150,914 arrived before the formal observing run had fully begun, but the detectors were operating in a calibrated state. The first signal was therefore both an astrophysical event and a severe test of the machines built to recognize it. Suspended beside the mirrors, you would not see debris pass through the detector. A gravitational wave does not carry stars outward like debris from an explosion. It changes the measured separation between freely suspended objects as it passes. In one direction, space is stretched while the perpendicular direction is compressed. Half a cycle later, the roles reverse. By the time an astrophysical wave reaches Earth, the fractional change, called strain, can be extraordinarily small. The waveform contains a compressed history. During in spiral, its frequency reveals the orbital pace. The way that frequency accelerates depends strongly on a combination of the masses called the chirp mass. Spin can alter the phase and precession. The peak marks the nonlinear merger. Ring-down frequencies describe the final object's mass and spin. A few seconds of data can contain the last moments of an orbit that evolved slowly for far longer. Multiple detectors improve localization and confidence. Arrival time differences place the source on the sky. Different orientations respond differently to the wave's polarization. A larger international network narrows the region and increases observing time. For events that also produce light, such as neutron star mergers, telescopes can search the localization area. Binary black holes usually offer no required flash, so the gravitational signal may stand alone. The waves also test general relativity. The in-spiral, merger, and ring-down must agree with one physical system. Analysts look for deviations, extra polarizations, or inconsistencies between the remnant inferred before and after merger. So far, observed signals have broadly supported the theory in the strong field regime, while precision and source diversity continue to improve. This is another answer to invisibility. A black hole need not orbit a luminous star, feed a disk, or aim a jet toward Earth. If it merges with another compact object, the changing curvature can carry its mass and motion outward as a wave. The horizon sends no light, yet the spacetime outside it records the collision. Strain is a ratio, not a fixed number of meters for every detector. A longer baseline turns the same fractional change into a larger absolute path difference, which is one reason LIGO's arms extend 4 kilometers. The laser compares the two directions continuously. Suspended mirrors behave as nearly free test masses over the relevant frequencies, while control systems keep the interferometer operating near its sensitive point. Analysts then ask whether the phase evolution is coherent, whether the same sky signal fits each detector, and whether independent search methods recover the event. The precision belongs as much to subtraction as to measurement. Seismic motion, thermal noise, scattered light, and quantum fluctuations are modeled or monitored so that the remaining chirp can be attributed to a wave crossing Earth. Orbiting far away, you would respond to mass rather than to the darkness of its surface. The most persistent black hole myth is unlimited suction. It imagines a black hole as a drain that pulls harder than any equal mass simply because it has a horizon. From a safe distance, that is not how gravity works. Replace an object with a black hole of identical mass, and the distant gravitational field remains essentially the same. Orbits respond to mass, position, and motion, not to whether the central body has a glowing surface. The sun example makes the point cleanly. If one solar mass were concentrated into a black hole, its simple horizon radius would be about 3 kilometers. Earth, still roughly 150 million kilometers away, would continue on nearly the same orbit. It would become dark and cold because the sunlight had vanished, not because the planet was dragged immediately into the center. Another myth gives every black hole a bright disk and jet. Most of the visual display requires matter. An isolated black hole moving through a sparse region may accrete so little that it remains extremely faint. A disk can appear when a companion supplies gas, a cloud reaches a galactic center, or a star is disrupted. A jet appears only in some accreting systems. The horizon alone does not guarantee a cosmic beacon. A third myth treats the event horizon as the location where gravity suddenly switches on. gravity changes continuously outside. The horizon marks causal escape, not the first appearance of a pull. One can orbit outside it under the right conditions, though stable circular orbits have an inner limit. Farther away, motion can be almost Newtonian. Closer in, relativistic corrections become necessary. Correcting these myths makes black holes more coherent, not less consequential. Their defining feature is compactness. Pack enough mass inside its gravitational radius, and the familiar field develops a one-way horizon. Everything dramatic nearby, heat, lensing, tides, time dilation, and waves, follows from that concentration and the matter available around it. What changes near a black hole is access. An ordinary star prevents matter from occupying orbits inside its visible surface. A black hole has no such material barrier, so gas can descend into a much deeper gravitational region before the outward path closes. That permits stronger relativistic effects and a more efficient release of orbital energy from the surrounding flow. It does not create extra mass at large distance. The distinction resolves the apparent paradox. A black hole can be ordinary in its distant gravitational influence and extreme in its accessible inner geometry. The same object leaves a planet in a far orbit while tearing apart a star that passes close enough. Distance, angular momentum, and the size of the horizon determine which description applies. Sending regular pulses, you would watch your connection to the distant station stretch and fade. Imagine a scientific probe falling toward a supermassive black hole with little surrounding gas. Choosing a quiet environment removes the lethal disk radiation and collisions so the thought experiment can isolate geometry. Far away, the probe fires regular light pulses. A distant station receives them at steady intervals. As the probe descends, the intervals lengthen and the wavelengths shift red. The probe's own clock continues. Its instruments do not measure a universal slowing of local time. If the horizon is large enough, the local tidal gradient at crossing may be modest. The probe passes the mathematical boundary after a finite reading on its clock. The distant station never receives a pulse, labeled after crossing, because no outward signal from inside has a path to the station. From the station's coordinates, the probe appears to approach the horizon ever more slowly. The final observable pulses become faint and delayed. In practice, the probe disappears from detection, rather than remaining as a crisp, frozen image. The radiation is overwhelmed by background and instrument limits. The statement that it freezes at the horizon is a shorthand for the coordinate behavior of signals, not a literal object suspended visibly forever. Inside the horizon, the probe can no longer choose a trajectory that increases its separation from the future singular region in the classical solution. Firing engines changes the local path, but not the causal destination. This is sometimes compared to the impossibility of choosing not to move toward tomorrow. The analogy is limited, but it emphasizes that the inward direction has become tied to the future structure of spacetime. No outside astronomer can verify the probe's later report. The thought experiment is derived from general relativity, not from telemetry recovered after a horizon crossing. That limit must remain visible in the narration. Physics can predict a consistent local passage in idealized geometry, while observation remains confined to the outside. The size of the black hole changes the physical danger at the boundary. A small stellar black hole concentrates the change in gravity over a short distance, so the difference between the probe's near and far sides can become destructive before or around horizon crossing. A supermassive horizon spans a much larger region. Its local tidal gradient at the boundary can be gentler, even though escape is equally impossible once the boundary is crossed. This does not make a real galactic center safe. Accretion radiation, magnetic fields, and orbiting debris may destroy a probe long before geometry becomes the only concern. The thought experiment removes those environmental hazards deliberately. It asks what the horizon itself does, then keeps that theoretical answer separate from the conditions around an actual feeding black hole. Past the horizon, you could carry predictions inward, but send no measured result back. Classical general relativity provides mathematical extensions beyond the horizon. For a simple non-rotating black hole, the interior leads toward a singularity in finite proper time. For an ideal rotating solution, the internal geometry is more elaborate. But these solutions are not travel maps confirmed by probes. They are consequences of equations applied where curvature may eventually exceed the domain in which the theory can be trusted alone. The distinction between prediction and knowledge becomes sharper after the horizon. Outside, astronomers test orbital motion, lensing, ring size, accretion spectra, and gravitational waves. At the boundary, the causal structure is tested indirectly by the behavior of compact objects. Inside, no signal returns. A region can be part of a successful theory while remaining observationally inaccessible from the exterior. General relativity itself predicts its difficulty. In the simplest collapse solutions, curvature increases without bound at a singularity. Infinite density and zero volume are signs that the mathematical description has reached an extreme. They may describe a physical feature, or they may announce that quantum effects omitted from classical relativity must become essential. NASA's Anatomy Guide states this uncertainty directly. Real collapse is also less tidy than a textbook sphere. Matter rotates, fields move, and perturbations enter. The exterior tends to settle toward a compact description, but the internal evolution can be sensitive and mathematically complex. A complete account would need a quantum theory of gravity that joins space-time geometry with the rules governing matter at the smallest scales. No experimentally confirmed complete theory currently fills that role. The honest sentence is shorter than the imagery often used. We do not know what matter ultimately becomes inside an astrophysical black hole. The uncertainty is not evidence for any particular exotic answer. It is a boundary around current measurement and theory. Even the phrase inside depends on the spacetime being described. For a stable non-rotating solution, diagrams can divide exterior and interior regions with clean lines. A black hole formed by collapse has a history. An emerging pair has a horizon whose shape changes with time. Rotating mathematical solutions contain additional structures that may be unstable under realistic disturbances. These distinctions matter to specialists, but none licenses a narrated tour based on direct observation. The robust exterior claims are stronger. Compact masses exist. Their horizons are consistent with relativity, and their surrounding light and waves behave predictably. The deeper equations provide disciplined possibilities. They do not convert inaccessible regions into measured landscapes. Keeping that hierarchy intact is part of explaining black holes rather than decorating them. At the end of the classical map, you would meet a limit in description rather than a photographed object. The word singularity often appears as though it names a tiny object sitting at the center. In the mathematics, it marks a failure of ordinary spacetime description. Geodesics cannot be continued in the expected way, and curvature quantities can diverge. Saying that matter is crushed to an infinitely dense point summarizes the simplest solution, but it should not be mistaken for a microscopic photograph. Singularity theorems show that under broad conditions, gravitational collapse leads to incomplete paths in general relativity. they do not provide a tested material model of the final state. Quantum mechanics governs particles and fields, while general relativity governs space-time on large scales. At a putative singularity, both are needed under conditions no laboratory can reproduce. Several research programs attempt to bridge the theories. They propose different structures, corrections, or replacements for the classical interior. Without decisive observational evidence, this episode will not select a winner. A calm explanation can leave a question open without filling the silence with certainty. The singularity is therefore useful as a warning sign. It tells physicists where a successful theory predicts its own limit. The same general relativity that explains planetary precession, gravitational lensing, time dilation, gravitational waves, and black hole shadows also produces a regime it cannot fully describe. The strength of the theory outside does not erase the limitation inside. Return to the title. The invisible object's greatest power may be conceptual as well as gravitational. It forces two foundational descriptions of nature into the same problem. The horizon can be modeled and observed through effects. The center turns that achievement into a question about what a complete physical law would require. A mathematical divergence is not automatically a physical infinity waiting to be photographed. Similar warning signs have appeared elsewhere in physics when an approximation was extended beyond its useful range. The correct response is not to erase the singularity from general relativity because it follows from the theory under broad conditions. It is also not to assign it a detailed material texture that the theory does not supply. The singularity theorems establish incompleteness of paths under stated assumptions. They do not reveal a tiny bead of matter or a doorway to another universe. A future quantum theory of gravity must explain why the classical description reaches this boundary and what replaces it, while also reproducing the exterior successes that have already been tested. That final requirement is easy to overlook. A deeper theory cannot merely offer an imaginative interior. At ordinary curvature, it must recover the general relativity that correctly predicts orbits, lensing, clock shifts, and gravitational waves. It must also fit quantum principles where experiments already support them. The black hole center is difficult because both inheritances matter at once. Many mathematical ideas can soften or replace the classical singularity on paper. Far fewer can connect every scale and produce a testable difference outside the horizon. Until such evidence arrives, the singularity remains a precise signpost in the classical theory and an unresolved physical question, not a completed description of matter's final state. Tracking a complete quantum state, you would ask whether every correlation survives the full evolution. Quantum theory treats information about a physical state as something that evolves according to strict rules. Classical black holes seem to hide the detailed state of infalling matter behind a horizon, while the exterior settles toward a description dominated by mass and spin. If the black hole later disappears through thermal Hawking radiation, a difficult question follows. Where is the information that distinguished everything that fell in? This is the black hole information problem. It is not the everyday question of whether a book remains readable after being destroyed. Physical information concerns the complete quantum state and whether evolution preserves it. The paradox emerges from combining quantum fields, horizons, and evaporation. Different theoretical approaches propose that information is encoded in radiation, horizon degrees of freedom, correlations, or a deeper description of spacetime. No direct observation of astrophysical Hawking radiation currently decides between these proposals. Large black holes are predicted to be extraordinarily cold, and their quantum emission would be overwhelmed by the surrounding universe. Arguments, therefore, rely on mathematical consistency, thought experiments, and connections to candidate theories of quantum gravity. The field has made substantial conceptual progress without producing one universally settled experimental answer. The horizon plays a double role. In classical relativity, it prevents outward communication. In quantum theory, fields near that boundary contribute to predicted thermal radiation. Attempts to preserve both a smooth experience for the infalling observer and unitary information for the outside description create tensions. These are technical problems, not evidence that a traveler would watch information written as visible symbols on the horizon. The useful conclusion is epistemic. Black holes are not only objects to catalog by mass, they are laboratories for testing whether our most successful theories fit together. The information problem remains important precisely because neither general relativity nor quantum mechanics can be casually discarded. The conflict becomes sharp because both theories carry principles supported far outside black holes. Quantum evolution preserves correlations in its standard formulation. Classical horizons prevent interior signals from reaching the exterior. Hawking's calculation gives the outgoing radiation a thermal character, apparently stripped of the detailed state that formed the whole. If evaporation completes in that form, the descriptions seem difficult to reconcile. Proposed resolutions alter how information is encoded, how the horizon is described, or how spacetime emerges. The episode does not need to choose among them. The observational fact is more limited. Astrophysical horizons have not yielded a direct measurement of Hawking radiation, and no experiment has watched a black hole evaporate. The paradox is a demand for consistency between theories, not a recorded disappearance of information in a telescope. Waiting beside a stellar black hole, you would find the predicted signal buried beneath your warmer universe. In the 1970s, Stephen Hawking showed that quantum fields in curved spacetime lead a black hole to emit radiation with a temperature. The prediction is often illustrated with particle pairs near a horizon, but that picture is an analogy rather than the full calculation. The central result is that the black hole can lose energy, and therefore mass, over immense time through what is now called Hawking radiation. Temperature decreases as black hole mass increases. A stellar mass black hole is predicted to be far colder than the cosmic microwave background today. It absorbs more ambient energy than it loses through Hawking emission. A supermassive black hole is colder still. Directly detecting this radiation from known astrophysical black holes is therefore beyond present capability. The prediction is respected without being mislabeled as an observation. As the universe ages and the background cools, an isolated black hole would eventually enter a net evaporation era in the standard theoretical picture. Mass loss would be exceedingly slow for large holes. Because the temperature rises as mass falls, the process accelerates near the end. The final stage depends on physics at energies where the semi-classical calculation may no longer be sufficient. The timescales exceed stellar history by vast factors. Ordinary stars will be gone long before stellar and supermassive black holes finish evaporating under these predictions. In far future cosmology, black holes become some of the last large reservoirs of organized mass energy, releasing it gradually into an increasingly dilute universe. Hawking radiation does not overturn the classical statement in the ordinary way. It is not light climbing from a known event inside the horizon to report what happened there. It is a quantum effect associated with fields and the curved spacetime of the black hole. Nothing, not even light, escapes outward after an ordinary classical crossing. The evaporation prediction belongs to a deeper description of the whole system. Mass sets the scale in the opposite direction from ordinary intuition. Larger black holes have larger horizons but lower predicted Hawking temperatures. Their enormous size makes their quantum leak weaker, not brighter. Known stellar and supermassive black holes sit in environments filled with warmer radiation and matter, so absorption dominates the theoretical loss today. This is why direct detection has not followed from decades of X-ray and radio astronomy. Those instruments observe accretion, jets, and surrounding plasma, all much louder than the predicted thermal signal. Laboratory analog systems can explore mathematical features related to horizons, but they are not detections of an astrophysical black hole evaporating. The distinction preserves the importance of Hawking's result while keeping prediction separate from observation. Watching a microlensing event, you would measure brightening without seeing the compact lens. Most confirmed black holes are linked to stellar collapse, accretion, and mergers. Primordial black holes would be different. They are hypothetical objects formed from unusually dense regions in the early universe, before stars existed. Depending on the formation conditions, their masses could span ranges unavailable to ordinary stellar remnants. No primordial population has been confirmed. The hypothesis matters because some primordial black holes could contribute to dark matter. A sufficiently long-lived population would add gravity without emitting ordinary starlight. But the idea faces constraints from microlensing, cosmic backgrounds, gravitational waves, and other observations. The allowed ranges change as surveys improve. It would be incorrect to say that dark matter has been identified as primordial black holes. Microlensing offers one search method. When a compact object passes near the line of sight to a background star, its gravity can temporarily magnify the starlight. The lens need not shine. The duration and shape of the brightening contain information about mass and motion, though degeneracies make individual identification difficult. NASA's Roman Space Telescope is expected to expand such surveys and may test populations in new mass ranges. Very small primordial black holes, if they once existed, may have evaporated through Hawking radiation before the present era. Searches for final high-energy signatures place additional limits. More massive examples could survive. Each statement is conditional because both the formation and radiation belong to theory being tested against absence or presence of signals. Primordial black holes belong near the end of the episode because they reveal how the word black hole spans different confidence levels. Stellar and supermassive examples are established through several observations. Intermediate examples are emerging. Primordial examples remain hypothetical. One name does not make every proposed origin equally proven. A microlensing event supplies a temporary brightening rather than a direct portrait of the lens. The geometry can be modeled, but mass, distance, and relative motion can trade off against one another. A planet drifting without a star and an Earth-mass primordial black hole could therefore produce similar durations under some conditions. Population statistics and additional measurements are needed to separate them. NASA's Roman mission is expected to monitor dense star fields with the cadence and precision needed to expand this census. A discovery would still require ruling out ordinary compact objects and free-floating planets. A non-detection would narrow parts of the allowed population rather than prove that no primordial black hole of any mass exists. The hypothesis spans many mass ranges, and each range meets different observational constraints. Other searches cover different parts of that range. A primordial population could alter gravitational wave merger statistics, contribute to background radiation through accretion, or reveal itself through high-energy emission if sufficiently small members evaporate. Each absence removes combinations of mass and abundance rather than the entire idea. This produces a patchwork of allowed and excluded regions that changes as models and surveys improve. The calm conclusion is neither discovery nor dismissal. Primordial black holes remain a disciplined hypothesis with observable consequences. Their status is weaker than the status of stellar remnants, Sagittarius A, M87, or gravitational wave merger remnants, because no population has yet crossed the same evidentiary threshold. Reading the mass distribution, you would find several possible histories written over one another. Black holes enter cosmic history through collapse, accretion, and merger. Stellar remnants appear after massive stars live and die. Some join binaries and merge. Dense environments can assemble heavier objects. Galactic centers accumulate gas and central masses. By the time astronomers observe the early universe, some quasars already contain supermassive black holes, creating a timing problem for how quickly the first seeds formed and grew. Growth cannot proceed without limit at every moment. Radiation from accretion pushes on the surrounding gas. Outflows reduce the supply. Galaxies run out of readily available central material or rearrange it through mergers. Feeding becomes episodic. A black hole can spend long intervals quiet, then brighten when a cloud, star, or new galactic interaction supplies matter. Mergers carry their own history. The spin and recoil of a remnant depend on the masses and orientations of the pair. Asymmetric gravitational wave emission can give the final black hole a kick. In extreme conditions, the remnant may move through the host nucleus or even escape a smaller galaxy. The object that seems like a fixed galactic anchor can itself be displaced by geometry released in a collision. Over still longer time, stars fade, galaxies change, and black holes may continue to merge or remain isolated. Standard far future models eventually leave them in an expanding, cooling universe where Hawking evaporation becomes relevant. This is a theoretical extension over times no observation can follow directly. It connects a horizon born in stellar collapse to a final quantum question at the far end of cosmic time. The history is therefore not a single descent into darkness. Black holes convert, measure, and preserve parts of cosmic change. They record stellar deaths in their masses, galaxy encounters in their growth, binary histories in their spins, and the geometry of mergers in their outgoing waves. Invisible does not mean disconnected. The earliest supermassive examples make this history difficult to compress into one root. A small seed requires sustained growth to reach billions of solar masses while the universe is still young. A heavier seed reduces that demand, but requires a mechanism capable of forming it. Dense stellar systems, direct collapse of gas, repeated mergers, and periods of unusually rapid accretion remain parts of the discussion. Observations of early quasars establish the endpoint without yet identifying one universal beginning. Later galaxies add another complication. Growth is episodic and tied to the availability of central gas. The present mass distribution is therefore a layered record with missing pages. Each new high redshift measurement, merger catalog, and quiet galactic nucleus constrains a different part of the sequence. Looking back across the evidence, you can now separate every measured exterior from the unresolved interior. We have talked about an event horizon that is not a solid surface, but a boundary in cause and effect. Outside it, light can still choose paths that reach distant space. At it, the outward route closes. Inside it, every future directed path remains within the black hole. Nothing, not even light, returns through that classical one-way edge. We have talked about 3 kilometers per solar mass, the quiet ruler that connects a city-scale stellar horizon with a supermassive horizon spanning a planetary region. We have talked about the collapse of massive stellar cores, the binaries that reveal unseen companions, and the gas disks that convert orbital energy into heat before matter disappears from view. We have talked about X-rays from million-degree flows and hotter tenuous coronae. We have talked about tidal gradients that can tear a star apart, and about the difference between the violent horizon of a small black hole and the gentler local crossing of a large one. We have talked about clocks that disagree because they follow different paths through curved spacetime. We have talked about shadows larger than horizons, photon paths that loop before escaping, and the far side of a disk lifted into view by lensing. We have talked about spin dragging nearby spacetime, magnetic fields organizing plasma, and jets carrying energy from a compact central system into lobes beyond a galaxy's bright center. We have talked about 4 million suns at the center of the Milky Way, measured through stellar orbits, and 6.5 billion suns in Messier 87, measured from 55 million light-years away with an Earth-sized virtual telescope. We have talked about a 142 solar mass merger remnant occupying the once missing middle of the mass ladder. We have talked about September 14th, 2015, when two dark bodies announced their merger through a rising change in the length of interferometer arms. We have talked about Inspiral, common horizons, and ringdown. We have talked about spacetime becoming its own messenger, carrying the mass and motion of black holes that needed no luminous disk. And we have talked about the boundary of the answer. General relativity predicts an interior singularity, but also signals its own limit there. Quantum theory predicts Hawking radiation, but no astrophysical black hole has yielded a direct detection of that faint emission. The information problem remains unresolved. Primordial black holes remain hypothetical. The unknowns are not empty spaces to fill with confidence. They are part of the measured map. The title can now be answered without metaphor. A black hole is among the most powerful invisible objects because an extreme concentration of mass reshapes spacetime, places a one-way boundary around a region, and lets nearby matter release enormous energy before crossing. Its spin and magnetic environment can support jets. Its mergers release gravitational waves. Its effect on stars, gas, light, and clocks can be measured even when the horizon itself returns no image. Its power is not unlimited reach. It is concentrated geometry and efficient conversion. Its invisibility is not an absence of evidence. It is a condition that makes the surrounding universe speak on its behalf. At the edge of the final picture, you would see the darkness defined by everything that remains visible. There's a particular stillness in the final picture. At the center, the black hole offers no ordinary surface. Around it, almost nothing is still. Gas circles and heats, magnetic fields twist, light bends into repeated images. A star advances around an invisible focus. A binary loses energy and quickens. Mirrors on Earth move through a distance smaller than a particle, and from that change, an event more than 1 billion light-years away becomes measurable. The black hole is drawn by everything around it. By a companion star leaning toward an unseen mass. By X-rays leaving a hot inner disk. By a jet extending beyond its galaxy. By clocks that no longer agree. By a ring assembled from radio observatories across Earth, by spacetime arriving as a chirp. The object remains dark, but the evidence does not. This distinction matters beyond astronomy. It is possible to know a thing without receiving a direct portrait of its interior. Knowledge can be built from constraints, from repeated consequences, from independent measurements that meet at one explanation. The orbit and spectrum agree. The ring size and mass agree. The inspiral and ring down agree. A black hole is not accepted because darkness invites imagination. It is accepted because the visible universe behaves with remarkable consistency around the invisible mass. At the same time, consistency has a boundary. The horizon prevents an outside report from the interior. The singularity marks a place where classical equations become incomplete. Hawking radiation joins gravity to quantum fields, but remains too faint around known astrophysical holes for direct confirmation. The information problem asks what a complete theory must preserve. Each unanswered question is attached to a clear reason it remains unanswered. That is a stronger ending than a fictional journey through the center. The honest map contains a region no telescope can return. It contains equations trusted through every strong field test we can make, and it contains conditions where those equations request a deeper theory. It contains observation, prediction, and uncertainty in the same frame. Far from a black hole, gravity resumes a familiar scale. A planet can orbit, a star cluster can continue through the galaxy. The black hole does not pull every surrounding object inward. Distance still matters. Angular momentum still matters. Matter must lose energy before it descends. The cosmic vacuum cleaner was never the right image. Close to a feeding black hole, the story changes. Gas gives up orbital energy and becomes luminous. The disk reaches temperatures that produce X-rays. A tenuous corona raises photon energies further. Lensing reveals the far side. Doppler beaming weighs motion with brightness. A horizon only tens of kilometers across can command the structure of a binary. A horizon on planetary scale can sit beneath a quasar visible across the universe. And when two horizons meet, their final orbit is not silent. The changing geometry travels outward. It crosses galaxies, voids, and 1 billion years of expansion. It passes Earth. Two long instruments record the same brief pattern. Mass that emitted no light has placed its signature in distance itself. This is the meaning of powerful in the title. Not intention, not hunger, not a force that ignores distance. Power as the ability of compact mass to change the available paths of matter and light. Power as orbital energy converted into radiation. Power as rotation connected to magnetic fields and jets. Power as two dark objects releasing a measurable fraction of their mass energy into waves in spacetime. And this is the meaning of invisible. Not absent. Not imaginary. Not unknowable in every respect. Invisible as a horizon that emits and reflects no ordinary light. Visible through the disk that has not crossed it. Visible through the star that continues to orbit. Visible through the photon that arrives bent. Visible through the wave that changes a detector. Nothing, not even light, returns after crossing the classical horizon. Yet outside it, the universe keeps a record, an orbit, a spectrum, a shadow, a ring, a delayed pulse, a rising chirp, one boundary, many measurements, and beyond that boundary, a question held open by the laws that brought us this far. Good night.